So question 5.12, steam is flowing steadily into an adiabatic turbine. The inlet conditions of the steam are 6 megapascals, 400 degrees Celsius, and 90 meters per second. And the exit conditions are 40 kilopascals, 90% quality, and 55 meters per second. Mass flow rate is 18 kilograms a second. We want to determine change in kinetic energy, power output, and turbine inlet area. So last question we did, I think it was 5.10, we sort of looked at how, in the case of a compressor and a turbine, if we're not told anything about speeds and velocities, inlet, outlet, we're going to assume the change in kinetic energy is negligible. But in this case, we're explicitly told it's not negligible because there's 90 meters per second, 55 meters per second, and we're asked to find exactly that change in kinetic energy. So in this case, we will include that in our calculations. So first things first, determine the change in kinetic energy. It's simple enough. We go here. We know that kinetic energy is m dot v2 squared over 2000 minus v1 squared over 2000, like this. If we plug in all the values given, we have 18 kilograms per second was the mass flow rate. V2 was 55 meters per second over 2000. V1 was 90 meters per second squared over 2000. Let's see what we get from here. 1855 squared over 2000 minus 90 squared. And I'm getting, typo. Okay, I'm getting minus 45.68, and this is kilowatts. That's kilowatts. So what was the next question? Next question was, oh yes, the power output. So power output, well, again, we're going to need to start looking, like in the last question, we're going to look at the first law of thermodynamics. We know this is a turbine, so Q dot is 0. We're going to have minus W dot equals M dot H2 minus H1 plus V2 squared minus V1 squared over 2000, right? Okay, so what do we know here? Well, we're trying to find W dot. We just found M dot. We also have all the information we need to find the per unit mass change in kinetic energy, right? It's basically what we found here, just divided by the mass flow rate. In terms of H1 and H2, what do we know? Well, we know the states. We're told enough information in both the inlet and the outlet to find the states. So we're all good to go to solve for W. We just need to start getting a bit specific about what H2 and H1 are. So let's start with H1. What do we have for H1? Well, the first state we're told is 6 megapascals and 400 degrees Celsius. And that we're told also it's steam. So we go straight to the steam tables. Here we go. We look at the steam tables for water at 6 megapascals, 400 degrees Celsius. We're going to look and see that the enthalpy, which is the third column, is 3177.2 kilojoules per kilogram. 3177.2 kilojoules per kilogram. Excellent. H2, what are we told? Well, we're told that the pressure is 40, and we're told that the quality is 90. So if there's a quality, by definition, we know that there's some quality that means it's a mixture, and we know the pressure as well. So we have to look for where the saturation pressure matches up, and then we look for a 0.9 quality. So we're looking for 40, I believe. Yes, no, that's 400. We want 40. There we go, 40. We're looking at this row here, and we can see that if we look in the enthalpy area over here, we want to go 90% of the way between this guy and this guy. So in other words, that's like saying HF, which is 317.59, plus 0.9 of HFG, which is this guy, right? 2319.2. And if we do that, we will get a value of 2404.87. 2404.87. And now we have everything we need to plug in and solve for the work. Now, again, by convention, first law of thermodynamics, we have this equation is minus W, but W can itself be positive or negative. And we said for a compressor, work is always negative. For a turbine, though, because the turbine it has work done on it by the fluid, it's a sort of an output, it's going to be positive work. So let's solve and let's see what we get, and let's hope we get a positive number. Otherwise, we've done something horribly wrong. So negative W equals m dot H2 minus H1 plus V2 squared minus V1 squared over 2,000. And let's see what W is. So 2404, 3177.2 plus 1 over 2,000 times 55 squared, that's 90 squared. All of this multiplied by 18 times -1 gives me a work output, which is a positive number, that's good, of 13.947 kilowatts. So, sorry, I'm off by a factor of 1,000 there. Sorry, excuse me. I'm getting work equals 13,947 kilowatts, which means it's about 13.95 megawatts. All right, so this is the power output of the turbine. And the last thing we're asked to find is the inlet area. So this isn't anything really new. We did this a few times in the other earlier questions of chapter 5. We know m dot, we know it's equal to area times velocity over specific volume. We want to solve for area. So that means area equals specific volume times m dot divided by velocity. So let's choose inlet or outlet, it doesn't matter. Actually, they're asking specifically for the inlet. So let's look at the inlet. At the inlet, we know the state, so we can find the specific volume. So let's just put it on the side over here. V1 equals, so this was 6 megapascals and 400. Here we are, 6 megapascals, 400. I'm seeing a specific volume, 0.04739. 0.04739 meters cubed per kilogram. That's good. Velocity at the inlet, we're told, is 90 meters per second. And m dot we've already calculated. It's given actually as kilograms per second, 18 kilograms per second. Plugging all this in, if all goes well, we should get an area of I'm getting 9.478 times 10 to the -3 meters squared.